Today, I'm pleased to introduce the session, Multimodal RAG with Milvus and GPT-4o, and our guest speaker, Jiang Chen. Jiang is head of AI platform and ecosystem at Zilliz. He's got years of experience in data infrastructures and cloud security. Before joining Zilliz, he previously served as a tech lead and product manager at Google, where he led the development of web-scale semantic understanding and search indexing that powers innovative search products such as short video search. He has extensive industry experience handling massive unstructured data and multimedia content retrieval. He's also worked on cloud authorization systems and research on data privacy technologies. Jiang holds a master's degree in computer science from the University of Michigan. Welcome, Jiang.
Hi, thanks for the introduction, Emily. Really excited to be here. So first, a short introduction of myself. My name is Jiang, and coming from the search and data infrastructure background, and right now I'm working on the ecosystem and developer experience of Milvus. Here's my email and LinkedIn and Twitter. So if you'd like to follow me on the social channels, I'll be really happy to connect and chat afterwards. So today's my sharing is about multimodal RAG with Milvus and GPT-4o. I believe many of the audience should have been hearing about RAG. The multimodal RAG is still kind of a new thing, and it has been vastly advancing in the past few months. And at Zilliz, we are the creator of the high-performant, highly reliable vector database called Milvus, and also the Zilliz Cloud, which is a fully managed Milvus on cloud. So that we have done a lot of research and experiments with the multimodal RAG, and we have seen this being applied in many of our customers' use cases. So today I will share about the background and history about multimodal, and specifically about the information retrieval around multimodal. And then I'll have a quick demo of the multimodal RAG with Milvus in action. So without further ado, let's jump right into the topic. So I think talking about multimodal, we have to talk about the information retrieval, because this is kind of the starting point of why multimodal has been so interesting. So the information retrieval at the multimodal setup was kind of started from CLIP, which is multimodal, which is an architecture that can embed both the text model of information and image model of information into the same semantic latent space. And so that using this approach, we can search, say, an image with text, and we can do the opposite, which is to search text based on image. And the idea behind this approach was to pretty much aligning the text encoder and image encoder into the same latent space. And what precedes this was that there was machine learning model, or specifically deep learning models, that can classify images into different semantics. However, the limitation of that is that you can only predefine a finite list of categories to classify into. Say, for example, you can define a cat, car, dog, and a limited list of semantic, and then you can train a model so that the classifier can detect like with what probability this picture looks like a dog or a cat. However, this has this limitation because it's not so flexible in practice. A lot of times we just want to know the semantic of the image without a kind of predefined list of semantics to start with. So that with some smart and careful training techniques, the CLIP model can align the text encoder and image encoder. Specifically, it can kind of aligns the generated vector embedding of both models into the same latent space, so that if the information or the semantic behind a piece of text and a picture of something, and they will have a very close distance in the latent space. this approach doesn't necessarily grasp the essence of the semantic behind the image. To my understanding, this is more of just aligning kind of two distributions into one. And another limitation of this approach is that it only supports searching the other, searching one dimension. It only supports searching from one modality of information. For example, if I want to search a piece of text plus an image, this architecture won't do that. So that with this as a foundation, there were improvements and newer researching on how do I conduct information retrieval both on text plus image information. And then sorry, before we jump to the next stage of information retrieval with multimodal, a concrete example of what Clip can do is here. So given an image, for example, it can classify the image into a set of semantics and then only output the correct semantic with the highest probability. For example, the closeness of this picture of an airplane between a list of semantics, such as a photo of a bird, a photo of a car, the model is trained so that it aligns the vector of this picture to the text piece, a photo of an airplane, and then make sure that they has the closest distance in the latent space rather than with the other incorrect semantics. So as mentioned previously, this approach is kind of training a classifier rather than a something that can essentially grasp the semantic of either image or text or even more text plus image data. And another nuance about this model is that it actually requires two models to do this cross-modality search. You need to embed the text with the text model and image with the image model, even though together they form a pair of clipped models. And so that the newer approach is actually to both combining the encoding of image and text data, and also applies some smarter training techniques to make the model better grasp the semantic behind those information. So a representation of this model is called Vista, and the model trained with this approach is called visualized BGE. This is a work done by a research institution, and the novelty about this is that it establishes the in-depth fusion of text and image data compared to the previous approach. It can actually fuse the information from both image and text, as well as it can still work for solely image data or text data. And another property about this thing is that it kind of preserves the strong performance of the general purpose text embedding that which it utilizes in this model architecture. So here is the visual illustration of the model architecture. So a typical example is that it's given both image and text data, which we call multimodal data here. So with the image data, it uses the vision transformer encoder to kind of extract the token representation of this image. So a metaphor for this, an analogy for this is like it kind of converts the image into a text representation of the same information. Not exactly, but to some extent is kind of doing this thing so that it converts the image represented as a set of pixels into a set of tokens, which actually carries some which carries the information represented by tokens that the pre-trained text encoder can actually comprehend. And for the text data, there's nothing special. It just uses a regular text tokenizer to tokenize the text into a set of tokens. And then what's magical here is that it actually concatenate the tokens of the visual content and the tokens of the text content expressed in natural language, and then use the pre-trained text encoder to encode this information into one single vector. And what's generated after this can grasp the semantic behind both the image and text, and moreover, it kind of combines the semantic of the image and text so that it can do this combined image and text retrieval. So with this architecture, it overcomes the limitation of CLIP, which can only accept one modality of data, even though the model itself is kind of a cross modality. And because the text encoder used here is a general purpose text embedding model, so that it can also can inherit the good capability of understanding the semantic of everything in the world. So instead of just mechanically aligning the embedding encoding of image and text, it can actually do a better job on comprehending the semantic behind the image and text. And here we have a concrete example on the capability of this model. This is also an illustration of how the training data is generated offline. But let's look at this example here. So the purpose of this model is that given a piece of text which is either related to this image or is kind of a piece of information that describes how do I want to edit this image so that the retrieved result will look like the edited image. So for this example, it actually just describes this image, which describes it as man on a balcony metal print by some artist. And if we just input this into the visualized BG model, it will actually retrieve something similar to this image, because pretty much they are talking about the same thing. It's not really adding any extra information. So that's not really so interesting. What's interesting is that if the image is actually described, if the text is actually describing something slightly different from this image, but also related to this image. So both the purpose of this model is to retrieve such kind of information, and the training, so that the construction of the training data also aligns with this principle, so that it uses large language model and video and visual content generation techniques to construct synthetic data to help train to help construct the training data set. So it does this by first collect a list of images with caption, which describes what the image is about. So this comes from an existing data set. And then it develops a piece of prompt, which lets large language model to be creative on altering the content about the image. For example, in this example, the altered information is still man on a balcony, but with a flock of birds. So with this, it generates another synthetic image with the information about this, and then and also using the large language model to summarize the new image caption into editing instructions, kind of simplify it and shorten it. And then use a filter to filter out things that doesn't really make sense. And then what's left are synthetic data sets of a piece of content and an image which describes what the image is about. So with this technique of constructing training data set, it is able to produce a large amount of samples for training, and then only with this large scale of samples is it possible to train a piece of model that can reliably do the job that we designed at the beginning, which is to retrieve a piece of content based on both the image description and the image itself. So this is one of the approach in multimodal. The other approach developed by Google recently has a arguably even more impressive results, and it applies the training techniques by utilizing the data at web scale by scripting the data from the public web, and then do data mining to produce the training data set. I will go over the training technique in a bit, but let's look at some of the impressive results from this model. So with the similar idea, which is given a query image and a piece of instruction expressed in natural language, it is able to find the image which kind of express the combination of the information from both of the modalities. So the first example is that I just want to find the identical image, which is pretty much I don't want any editing instruction on this, and then it is able to retrieve the exact same image. So this indicates that it has a pretty good baseline, which is not doing anything interesting. But what's interesting is that given an instruction of compare its height to the world's tallest building, it is actually able to retrieve a piece of image which shows the height comparison of similar architectures of similar buildings. And this is very impressive compared to the other multimodal retrieval techniques, which can only, so this one just shows another individual building, which like looks similar to this, which is also a skyscraper, but it is not as close as this one in terms of the semantic closeness to the combination of both the image and text information. And this is even more impressive, which instructs the model to find something, some picture which is which is looking from inside of this building. I'm not sure if this is exactly the picture of the view from this luxury hotel, but it looks like it is able to kind of exclude information like this, which looks like the same building, but is looking at the building from the outside of it. And then the other one, I think it actually grasps some of the essence of the information here, or it has some kind of intelligence here, which is to find the other attractions. I think this hotel is in UAE, so this is probably the Palm Islands, one of the famous attraction in UAE. So with this, it kind of indicates this model actually have some intelligence in reasoning, and also kind of comprehending the semantic behind the both the image and the instruction pretty well. And in order to train a model like this, it requires a substantial amount of data, which are either manually labeled or mined from the larger data sets, such as the World Wide. So Google actually utilized their deep expertise in managing the web scale data. So the way that they construct the training example is by first crawling some of the public web pages HTML, and then extract the images in the same web page. Because they are in the same web page, so that semantically they are close to each other, or they have some kind of connection between each other. And then it uses a vision large language model to generate the instruction regarding it uses the large language model to comprehend the text description in this web page, so that given it is all of the information resides in the same web page, it's very likely that the text is describing the relationship between two images appearing on the same web page. So in this case, it is actually able to find the text piece from the web page, which describes that the bottom picture is a battery or a charger. Actually, it's a charger of the camera on the top, and then it uses a large language model to rephrase and summarize the text piece from the original web page to generate the instruction, which describes with what text piece in this bottom and this top page you will a human being can refer it to the bottom picture. And then this process is done in a large scale by scraping the whole World Wide and doing more sophisticated grouping and cleaning, so that similar images with similar semantic are grouped together, and then it generates the instructions as described previously. And then eventually it is able to generate a large set of high quality training data, which looks like, so we can see this example here, which describes with what kind of transformation or editing the right image will matches the left image or vice versa. And then during the training phase, it uses the left image and the instruction to find the image on the right, and with correction and large scale of training, it is able to distill this information into a language into a embedding model that can achieve this job. So that this is kind of the theory behind multimodal retrieval. And to apply this in reality or in production, we actually need to find a piece of infrastructure that can store the vectors generated from those multimodal embedding models and retrieve them efficiently at scale. And also, moreover, we can apply this information retrieval stage into the large language model generation phase, the so-called retrieval augmented generation approach. Just instead of a typical a traditional retrieval augmented generation, which only retrieves text information and then send it to large language large language model. This approach can actually retrieve the image information and then send it to a vision language model or a multimodal large language model, and then do interesting applications. So in terms of the vector storage and retrieval, we can use Milvus, which provides kind of two forms of deployment. It has the lightweight Milvus Lite, which can be deployed locally on laptop or notebooks. And in today's demo, we'll actually use Milvus Lite to showcase this image multimodal retrieval and multimodal generation. And it also has a more performant Docker and Kubernetes deployment, and also fully managed Milvus on this cloud, which is more suitable for larger scale of retrieval workflows. And the Milvus project is also integrated with many frameworks in RAG. For example, in Llama Index, there's a multimodal retrieval component, and working with the frameworks in the open source community, this makes it easier to develop more comprehensive RAG and other AI-powered applications. Once chosen the infrastructure stack, we need to design a data model that can fit the multimodal information into a database, like Milvus vector database. And there are two ways of designing this model, depending on what kind of retrieval model you are using. For example, if you are using single modality of embedding models, you can still do this workload by applying hybrid search technique here. So the way it works is it actually stores the vector embedding of image and text separately. And this can be the vectors can be generated by two embedding models. In this case, for example, you could have a vision transformer, which is only able to comprehend visual content. And then you can use the traditional text embedding model to embed the text information. Or you could use clip and then store them in separate vector fields. And during retrieval time, you will actually embed the target information. For example, you could have two pieces of target information. One is in text, the other one is in image. And then you can embed them separately and then have two query vectors, and then query those two vector fields separately, and then combine them by merging techniques such as reciprocal rerank function or weighted rerankers, and then merge them into one single list by, say, you could merge them by RF and then have a list of IDs. And then with that information, you can combine them and then present it in your application's UI, or you could send them further to multimodal large language model to do other comprehension. The other techniques is actually to use a multimodal model that can take both text and image information as input and then embed them into one single vector. And so this vector actually combines the information or semantic behind both pieces of information. And then during search time, you don't need to do hybrid search anymore. You just need to use the same model, supply the query image and query text piece to the embedding model, and then generate one single query vector, and then just do a plain vector search in Milvus. A slight variation of this is that if you use clip model, which technically are two models, you can still do this, but you need to be a bit more careful on defining the identifier of this of each entity. For example, this data structure can be is either there's one field which is either image URL or text, and then you can you pretty much treat the image and text as two different information, and then store them in different rows. And then for each row, it can be a vector of either text or image. And then during search, you can still search on the single field, single vector field, but the return result could be either text or image. For some of the application, this actually makes sense, but be careful to align the data structure design to your application's requirement. Okay, so let me check questions before I jump into the live demo. Okay, I think we're good here.
We have just one. I think it means how does I think it means pre-trained. How does the pre-trained text encoder understand the semantics of both image and text?
Okay. Going back a bit to the training phase. So in the training phase, actually I won't say it has the ability to understand the text and image. It is actually through the training purpose, we're aligning its distribution towards a symptom, so that it looks like it has the ability to comprehend the semantic between image and text. So I will let me give some intuition behind this. So it's just like by looking at an enormous amount of examples, a human being can learn something, so that the large language model, the deep neural network model training process is kind of mimicking this process. So that as long as the training data aligns the labeled output to the input. For example, the training data pretty much tells the model that, okay, looks like this. So with this image, which is an island in the water, given this piece of text, same island when it's sunset, you're supposed to point out this image. So that just by repeatedly doing this, it is able to kind of approaching the state where it looks like it has understood the semantic behind both the image and text. So this process is kind of general to any kind of training in deep neural network. What's special about this one is that it designs the model architecture so that it can take two pieces of information as input and then aligns the output to not only one modality of the input information, but a combination of information from both of the two modalities. I'm not sure if that answers the question here. Feel free to raise a follow-up question in the Q&A. Okay, I'll jump to the demo here so that, okay, let me set up. Let me pre-run this so that we don't need to wait too long. So this demo is supposed to do a multimodal search. So here in this example, we have the image, which is a picture of a cat, and then an instruction in text, which is to find an earphone with the theme of this image. And then it is able to retrieve things like combines the semantic of both from the input. And specifically, I think this is the second best result returned from the retrieval. It's actually a pair of headset with the cat ears. So very close to our intention here. And then in this demo, I will present how do we implement this kind of multimodal retrieval. And at the end, I will have a GPT-4o to do re-ranking, which further enhances the results so that we wish the target result is actually ranked the first in the from the results. And GPT-4o is able to help us to kind of further enhance the retrieval quality. Before doing anything, we'll install a bunch of dependencies, including PyMilvus, which is the client library of Milvus, and the other utilities which we'll use to process the image and download the embedding model weights, and then do the inference. So we'll first, in this example, we'll use the BG visual model, which we introduced previously. And this model, in order to do inference on this model, we need to download this flag embedding framework, which is a convenient wrapper of this model. And we also need to download some image data as the pool of target candidates that we want to search from. So here we'll download the public Amazon reviews dataset. We'll also need to download the weights of the BGE visualized model. So as you can see, this model isn't that big. It only has about 300 to 400 megabytes. Okay, now with everything, let's build the encoder, which is a thing used to encode the text and image information into a single vector embedding. This uses the previous downloaded BGE visualized model. So formally it's called Visualize BGE English V1.5. Now we're able to load data. Let me try this. Okay, so here we're sampling 900 images from this dataset and then generate vector embeddings through this BGE visualized model. And once these are generated, we'll store all of the embedding model, all of the vector embeddings into Milvus vector database. And what happens here is that it actually reads the image folder and then samples 900 images, and then use this encoder image, which is an abstraction of the flag embedding framework. Okay, with all of the embeddings generated and stored in memory, now we can load them into Milvus vector database. So here we actually use Milvus Lite, which is pretty convenient so that you only need to specify a local file as they will persist the data into local files. And then you pretty much doesn't need to do anything other than defining the vector collection where you want to store data and then just ingest the data. So it works as, let me run this first. It works as you can see, it's pretty fast to ingest 900 embeddings. So it's not that big of a load. To start the Milvus Lite, you just need to import Milvus client from PyMilvus and then define some of the parameters like the dimension of the vectors, the name of the collection where you want to store the vectors, and then you just instantiate the Milvus client with a file, a name of the local file, milvusdemo.db. And then with this newly created Milvus client, you can create a collection with the specified name and dimension. And we'll also enable dynamic field here, which is used to store the metadata. If you want more efficient metadata filtering, which in some of the cases you will need it. For example, you want to do a semantic search on something, but only for things that specifies some criteria like published time is greater to something or the author is someone. If that's the case, then you can disable dynamic field and then define the schema formally. Say, you could define a data model like this. Like you can define published timestamp in the schema, and then create the we call it scalar index, which is the index of non-vector field. And then when you do the search, you can specify, I want the semantic similarity of something, but only specifying the published timestamp is greater than some Unix epoch. And by having scalar index, this can be done in a very efficient way compared to this dynamic schema, which doesn't really have this scalar index. But for convenience, let's just do this so that we can skip defining the schema formally. And then we'll just call insert on this client with all of the vectors generated previously, and then specify the collection name. And so all of the 900 vectors are ingested already. Okay, now we're ready to do a multimodal search on the data stored in our vector database. So let's select an image of leopard and then define the instruction as I want to have an earphone which looks like this image. And then we can encode this both piece of the both the text and image information with the multimodal embedding model, and then generate a single vector. And then we can use this single vector as the target vector and use Milvus search API to conduct the search. And then other than this, you just need to specify some parameters for the search. For example, what fields in the schema do you want this search to return? In this case, we care about the image path, which is here we treat it as the identifier of the image. And then the limit, which means which defines the top K, which is how many results you want the search to return. So in this case, 9 means we want the 9 candidate images that are closest to the target image in terms of semantic. And then you can define search parameters, which is kind of nitty-gritty details in vector search, such as the metric type, we want it to be cosine. There are also other metric types like IP. With this, we just need to extract the results from the retrieved images from the search result and then print them. So here, let's run it. So this prints the image path of the top 9 images, semantically similar to what's defined by image and text. Let's look at what they are. So here we combine the image into 5x5 panoramic view, and then also display the image which we use as target. So I will run this again, but here is what it looks like. So the left leopard actually is a 3x3 panoramic view. So on the left is a leopard image. On the right are top 9 images, which looks like this image, but also kind of carries the semantic of earphone. Let's run this again. Okay. Okay. Fun thing about live demo. So I actually ingest the data twice so that I'm seeing duplicates in the results. Let me see, do I have time to fix it? Actually, I do want to fix it. Let me do this. So I will just do a hack here by defining a different, let's say a different persistent file. So that's pretty much creating another Milvus vector database. And then I will ingest it again so that there won't be duplicates. Okay, let's run this again. Okay, here we go. So we have 9 unique images, which looks like a combination of the semantic here. However, if you look a bit closely, some of them do look more similar to our target, and some of them, so for example, this, it just looks like a pair of headset, but nothing special and related to leopard. It doesn't really have the fancy pattern of it. So let's use GPT-4o to do re-ranking. So GPT-4o is very intelligent in the sense that it can comprehend the semantic behind this image information. And actually, we have composed a piece of image which contains the target image and a set of images with their ranking. And so that in this instruction to the large language model, we tell it to do a re-ranking based on the semantic closeness to both the text and image. And let's see how how GPT-4 can perform in this workload. So most of the code are actually just for triggering GPT-4, and what's interesting here is that given the information which describes the background, and it specifically tells the model to provide a new ranked list of indices from most suitable to least suitable. And with this, let's do this generation from large language model. And let's also display the results here. So it actually returns this one, not so impressive in this case. And because there is some randomness behind the generation, let's see how it works in the second time. But for this one, let's see what kind of objective we are trying to achieve here. So we're pretty much having GPT-4o to do the reasoning, re-rank the 9 images on the right based on your understanding of the semantic of the image on the left, and then give the reasoning behind this. Because one kind of tricky technique behind large language model prompting is that if you let it kind of think out loud, it will usually do the reasoning a bit better. And so it does give the reasoning, which is it thinks the most suitable atom is number 2, and that's because it just looks more like an earphone, and then just carries the information from the image as well. We'll not read all of them. And let's regenerate this and see. Oh, actually, let's regenerate it here and see how it performs on the second time. Okay, so this time it does give a slightly different result, which I think is better than the first one. So that means it does have some, it is not always that stable in terms of the performance of the language model. But this time it does give a more reliable result, which, I mean, this pattern arguably is kind of similar to the pattern of the skin of leopard. And then it is definitely a pair of earphones. I'm pretty sure if I generate it again, it will likely give a different result. Okay, still the same one. So let's play with it a bit. So let's change the query to another one. So last time we were talking about earphone. And this time, how about we check about phone cases. So I want to have a phone case which looks like the pattern of leopard, but it is a phone case rather than an animal. Let's run this and see what happens here. So this time it retrieves some results, and I believe it will be pretty different results here. Okay, here we go. So the model does give a so pretty much all earphone, pretty much all phone cases, and well, from my human eyes, I think number 6 is actually a bit more promising because it has this beautiful pattern. So let's see if I mean this is already an impressive result, even though number 6 is not ranked the first. It's still kind of in a very limited set of results. It gives one promising result. We just need to make it go a bit further and then rank the first one to the top, so that we don't want to risk kind of showing some unrelated results to our end user. So let's do the same thing on re-ranking with GPT-4o. And then print the final result here. Okay, so this time, very impressive result. It does give this phone case, which is, first of all, a phone case, but also features a leopard print pattern that closely matches the intention behind both the text and image. Okay, that's pretty much what I want to share I'll check if there's any question from the audience.
We do have some questions. So clip is clip basically two models? Can you explain again how that affects how you do retrieval in Milvus?
Yes. So clip is a cross-modality model, which means it can map the information of both text and image to the same latent space. But actually, if you look at the detail, it does use two different encoders. So clip for image, it uses the image encoder, and text for text encoder. And those are actually technically two different models, and they have different model weights. So it affects the design of the retrieval system in two aspects. One is that in terms of the embedding phase, you need to load kind of two copies of model weights into your GPU memory. And that's pretty much using two models. And then for if you are given a piece of text, and then you can utilize one part of the GPU memory and uses this particular model to do the inference, otherwise the other. And that's one piece. The other piece is for the data storage. So this here, I actually didn't show how to store the embedding result of clip exactly, because if I were using clip, I'll probably use neither of them, and will very likely to design the model, data model as I'll have either image or text as a unique entity, and then I will identify them separately, so that the way that I design the data model is that I have the one single vector field, which stores the clip embedding vector, either from the text model or image model. And then I will have kind of a shared non-vector field. I'll probably call it image URL or text. And in this one, I will just store a piece of string. And the string can be either the raw text, or it can be the, say, URL of the image. And then I'll kind of decide what the type of, I'll probably have another field which defines the type of this piece of information, whether that's text or image. I'll use an enumerator to store that, or just a number to indicate. And then during ingestion time, I will first detect whether this is image or text, and then I will decide which model to use for inference, and then I'll generate a vector embedding, and then we'll store it in the field. And then based on whether it's text or image, I will store this one single field with the kind of representation of that information. The representation for image is URL, the representation of text is text.
So there's a follow-on to that question, which is, do you mean that clip encodes images into one vector space and it encodes text into a completely different vector space?
No, exactly not. It actually encodes, even though it uses two different model weights for encoding, but it actually encodes the text and image into the same latent space. That's why it can do this cross-modality search, which is you can search an image of dog from a piece of text called dog.
Great. Here's another question for you. How does GPT-4o know the schematics of our custom model? Is it because it understands the raw vector data, or the embedding types are the same?
Wow, that's a very good question. It actually does not. It does not understand the vectors. It understands the image pixels. So here, in this re-rank with GPT-0 phase, we actually send this literal image or a set of pixels to GPT-4, rather than say 10 vectors to GPT-4, so that it doesn't really know about vectors per se. But it's still pretty impressive because it can know First, there's a very complex instruction. Down below. There's a very complex instruction telling it, okay, you need to re-rank the stuff on the right of the image based on the semantic of blah, blah, blah. And secondly, it can kind of connect the information expressed in the instruction to this image and then comprehend this image. Well, this image is just a set of pixels. So I mean, to me, it's still pretty impressive that it can do this great job on, say, picking number 6 out of these 9 images. And even, I mean, the level of comprehending of the spatial information is also very impressive, so that it kind of knows, okay, here is aligned as so the is ranked as 0, 1, 2 rather than 0, 1, 2 like vertically. So that's kind of pretty, I don't know, futuristic already. And the other thing to mention is even though GPT-4o can do this very impressive job of selecting the semantically related content, doing at this scale will be extremely expensive. So that it, even though, I mean, seemingly this multimodal retrieval model doesn't do as good job as GPT-4o, it kind of still has a strong advantage, as you can do this at scale. You can kind of save time by paying some storage cost by doing this offline indexing using the cross-modality model to index the images into vectors and then store them in vector database. And then at retrieval time, the retrieval is kind of instantaneous compared to with GPT-4o only kind of selecting 1 from 9. I think last time it took about like 5 seconds-ish, 5 seconds to do this kind of generation or reasoning. However, for vector search, let's check, it's probably less than a second, because there are only 900 candidates to search from. Yeah, it's 0 second. Yeah, I mean, it's pretty fast. I believe it's just like 10 milliseconds or so. So that there's still a lot of benefit of applying the kind of the traditional technology of search, which is that you do a lot of work offline through indexing and then online during query serving time. This can be very efficient, very applicable to large scale serving. And then only for some highly valued use cases will it deserve for you to use GPT-4o and burning your cache on large language model tokens to do this kind of fine processing of information.
Thank you. There's a request of, can we make this demo code available?
Oh, yes. Actually, this is public available on Milvus website, so that you can go to Milvus docs, or you can directly jump into that by scrolling down a bit. We have RAG image search and also multimodal examples. So this will navigate you to a hosted kind of online demo, which you can play with it. And here in the docs, we do have the instruction on how to implement this yourself, which covers what I have just shown. And also, you can also deploy this with things like Streamlit, so that you can have a front-end experience. I just need to click on this, and then it will now get you to GitHub, so that you can deploy a demo with UI experience similar to this in your local laptop or notebook.
And we can go ahead and share those links out in the follow-up email with the recording as well. So keep an eye out for those.
Yes. And also through on this online demo, you can just try with a preset list of examples. For example, here you can search the toy of this machine, and then you can also do re-rank. which will shuffle the rank of the search results.
So we've kept everyone over a couple minutes. We've got one last question, and then we'll call it a day. Is there any image generation using Dolly-like LLMs in multimodal RAG? For instance, if you ask earphones like a leopard, it's only searching. Why is it not generating a completely new image using searched images of a leopard and earphones?
That's a long question. Let me.
It's in the Q&A box.
Yeah. So first of all, you can kind of have more creative way of doing this kind of demo by searching something, and then you can send the search results to a stable diffusion kind of model and then generate something out of it. Let me check what's the other part of the question here. It's like when you're asking your friend, like, answer why is not generating a complete new image using. And the reason that the demo that I showed before was not generating anything was because I wasn't telling it to generate. I was actually doing something a bit different than generation, which is, well, it's essentially it's also generation, but it's not generating new information. It's just generating a piece of text which tells me what's the best image out of the things shown in that 3x3 box, which matches the leopard image and my instruction best. So essentially, it's still generating insight, but not really generating another piece of the image per se.
So something we might see on like a e-commerce website, like looking for some specific type of product using different inputs, correct?
Yes. So a more creative way of doing this, well, in real world application could be you retrieve some images similar to this semantic expressed by both image and text, and then you apply your business logic to generate something so that you inspire the users, like inspire the user to buy something which is really interesting, or like drawing something for artists.
Jung, thank you so much for this great session. Thank you to all of you who have joined us. We will send out the recording as well as the links that he shared today. Thank you for staying up late. I know it's late in your time zone, so we really appreciate it. And we'll hope to see all of you on a future webinar. Thanks so much.
It's a pleasure. Thanks, everybody.